Hello, welcome to the holidays, time where I get to teach without any students. No students singing at me, no students rolling their eyes at me, no students piling up chairs and desks in front of the door, so I can't get back into the classroom. Anyway, we are talking about transformers today. What is a transformer, you might ask? A transformer is a device which changes voltage. So for example, if the voltage is increased by the transformer, then we call it a step-up transformer. Step up, and you can probably guess if the voltage is decreased by the transformer, then it is called a step down transformer. Okay, now the transformers aren't magical devices which break the laws of thermodynamics. They don't create extra energy out of nothing. So even if they're increasing the voltage, the overall power stays the same. Okay, and you might remember that power in an electrical device is equal to the voltage times current. So in order for the power to stay the same, if it's increasing the voltage, it must decrease the current in a proportional amount. And that goes the same for decreasing the voltage. It doesn't just lose energy out of nowhere, it's keeping the power the same by increasing the current as it decreases the voltage. I did this again. I wrote step up twice. The voltage is going down, it's a step down transformer. Down. There we go. Now, the amount of power saved is not perfect, right? Entropy is still a thing. Things are losing energy as they go. So, however, we're talking about ideal transformers at this point in time, which means that they are transforming all of the energy from one voltage into that same amount of energy at a different voltage. So how do they work? Well, let's look at the design of a transformer. Um, we have a power supply, AC power supply, and it's powering a solenoid, terrible solenoid, like so. Okay, and that solenoid, when the electricity goes into it, it turns the solenoid into an electromagnet. And that electromagnet has an iron core inside it. Sorry. And that iron core extends the magnetic field, extends and strengthens the magnetic field to make it go around another coil. Let's make it a blue coil. Another solenoid here, and this solenoid is connected to some device or something. Let's say a light bulb, even though this is a pretty silly idea. You wouldn't really have a light bulb connected to a transformer like this. You'd have some other device, but we'll get into that later when we talk about the applications of transformers. Now, how does it work? So this AC power supply is creating a current, and that current changes direction constantly. In fact, in Australia, our AC works at 50 hertz, so it goes up and down 50 times a second. Okay, so this part here is creating a changing current, constantly changing. Now, we know due to Lenz's law that whenever you have a changing current, sorry, nope, got to say one more thing first. That changing current is creating a magnetic field in here, and that magnetic field is also constantly changing. If we imagine that the current is going across this way, we can use the right-hand grip rule, making my fingers go in the same direction as the coils, um, there, and my thumb points straight up. So we know that there's a magnetic field going up. However, constantly changing current means that this magnetic field is also constantly changing. So we have a changing magnetic field here. Now we need to think about Lenz's law, and it tells us that with a changing magnetic field, then we get an induced EMF. Okay, this magnetic field is being extended all the way around this iron core. Okay, it's important to note that no electricity is flowing in the iron core. These wires here are all insulated. They are not directly connected to the iron. Also, this arrow I've drawn around the iron core is not an induced current, definitely not an induced current. It is a magnetic field. Okay, just like an electromagnet, it has a soft iron core. That soft iron core is not itself a wire conducting electricity. Okay, so in this coil here, we have a changing magnetic field. That changing magnetic field is going to create induced currents, okay, or an induced EMF. So we have electricity here, powering this coil here. That induces a current in this coil here. So we've got current going from one coil to another. Hooray. So what? How does this transform the voltage? Well, every loop of wire in this second coil here, well, the second coil, it's called the secondary coil, S. Every loop um, has the same change in flux going through it. Every loop of wire has a bit of induced EMF. You have 2 loops, you have twice as much EMF. You have 3 loops, 3 times as much EMF. The more loops you have, the more voltage you get out of it. The less loops you have, the less voltage you get out of it. So really, by increasing or decreasing the amount of loops, amount of coils of wire, you increase or decrease the amount of voltage. If you want to step up a transformer, you need many more coils in the secondary coil rather than the primary coil. If you want to step down transformer, more coils in primary, less in secondary. So it's a ratio of the two things, and that's where we get our equations from. This first equation right here, that was supposed to be in pink. This first equation right here, right, says that the ratio of turns, that's N is number of turns in the primary coil over the number of turns in the secondary coil is equal to the voltage in primary over voltage in secondary. So the voltage is directly related to the number of turns in coils. If you have 20 turns in the primary and 10 in the secondary, you have a step down where you have 20 over 10, which is equal to 2. That means that the voltage divided by the voltage is also going to equal 2, which means that you're halving the voltage. Okay, and this second equation here comes from the power that we were talking about down here. Okay, the amount of power in the primary coil is equal to the power in the secondary coil. Because it is an ideal transformer, it is obeying the laws of thermodynamics. Energy must be conserved. So V times I in the primary coil, that's just power in the primary coil, right? V times I. V times I in the secondary coil, that's power in the secondary coil. So this is really just a rewording of conservation of energy. It's just saying that the amount of power in the primary coil is equal to the power in the secondary coil. This is for an ideal transformer if no energy is lost at all. That's how they work. Now, let's talk about transformers in real life, not in the movies, not these ideal transformers, okay? So that's the limitations of the ideal transformer model. These equations here, those equations are a model. They're describing something theoretical, not describing something real. Okay, so one reason why they are a model and one limitation is incomplete flux linkage. This is saying that the magnetic flux, not all of it goes into the secondary coil. A lot of it is lost. Okay, a solenoid. So let's say if I draw a bigger version of the primary coil here, and you imagine there's a iron core inside it, right? The solenoid will create magnetic fields going around it like so. And you can see that a lot of that is not going in the direction we want it to. Only the stuff heading off to the right there is actually useful. The stuff on the left is pretty much lost. Now we want strategies used to improve the efficiency. So the the ferromagnetic iron core in the middle there is guiding a lot of the magnetic field so that it is going through the secondary coil. But it's definitely far from perfect. So what's the limitation? Some of the flux, changing flux, doesn't go through the secondary coil. What's the strategy used to try and fix it? We have the soft iron core moving, connecting the two coils together, guiding that change in flux. Okay, also resistive heat production. Okay, anytime you have current going through a wire, it loses energy to heat. As Ohm's great-grandfather once, as Ohm's dying uncle once told him, with great power comes great current squared times resistance. Where am I going to write that? With great power comes great current squared times resistance. And this is telling us that with the current going through a resistor, we're losing power to heat, okay? This is happening inside the two coils, but also we have eddy currents, okay? And as we learned from Lenz's law, eddy currents are induced currents caused by a conductor trying to create a magnetic field, and so it's going to have a small circular electric field, okay? And that circle is an eddy current, like eddies in water. Where are these eddy currents being produced, and what strategies do we use to improve efficiency? The eddy currents are being produced inside the iron core. So I said that this arrow is not representing electric current, and it's not, but there are still electric currents in the iron core because the iron core is in a changing magnetic field. It's going to experience that changing flux. It's going to have induced currents because of that, but we can limit them. So if we take shrink a cross section of this iron core and we draw it over here, let's give me some space. Okay, cross section, whoops, I want a brush. Here we go, cross section of the iron core here. The current is going, the changing flux is going in and out of that cross section. So if you think about how it's going to try and oppose that change, it's going to try and make its own magnetic field going in or out of the cross section as well. So the currents are going to be going across the face of it. So we're going to get eddy currents like this, producing magnetic fields coming out of the page. How do we reduce that? So we reduce that by having this piece of metal made up of tiny sheets that are all sandwiched together, right? Instead of drawing it like this, the face of it would actually just be one little sliver of metal like this, with a certain thickness like that. This metal will be coated and insulated, and then there'll be another piece of metal next to it like this. Whoops, this drawing is terrible, but hopefully you're getting an idea. If we have lots of sheets of metal all next to each other, they can still extend the magnetic field around from the primary coil to the secondary coil. However, we're not going to be able to create that large eddy current like we did before. Now, along the thinness of these, we can create lots of little eddy currents. Yep. There you go, that's not a terrible drawing. So it's that compared to this. This is our original one, right? In our original one, we have a nice big eddy current creating a nice big magnetic field coming out. In here though, it can't cross from one sliver of the iron to the next sliver of the iron, okay? So instead, you just get tiny little eddy currents all along the inside of this. They end up being much, much weaker than one big eddy current, and each of them creates little tiny magnetic fields coming backwards, not really opposing it very well. So that is, and we call this laminated iron sheets that have all been pressed together to create the soft iron core. Laminated iron sheets. This here, this is one laminated iron sheet. It's a piece of iron, it's been laminated so that current can't flow from it into the next one across. Okay, last bit, applications of step up and step down transformers, including the distribution of energy using high voltage transmission lines. So let's go back to what Ohm's dying uncle told him. Hopefully you realize that's a Spider-Man reference. You probably don't. So Ohm's dying uncle told him that with great power comes great current squared times resistance. Okay, and I just told you that says every time you have current in a wire, in a resistor, you're going to lose power to heat. Okay, this is true in the power lines that transmit our electricity from the power station to our homes, right? These are electrical wires on poles. Hope you recognize that. Okay. In Sydney, right, we have two big coal power plants. One's about 120 kilometers away, another one's about 200 kilometers away. All that electricity has to travel all those hundreds of kilometers to get to us. As it travels through, with the resistance of the wires, it's losing power. So one way to deal with that is to lower the resistance. We use wires made out of aluminium or copper. Copper is better, aluminium is cheaper. It's a sort of payoff. If we use the cheaper aluminium, we need the wires to be a bit thicker so that they have lower resistance, etc. However, notice this squared, right? They're always things worth paying attention to, current has a bigger effect on power loss than resistance, okay? Because as you increase the current, it's the square of that difference, which is how much power you lose. So you want really, 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 really low currents in your wires. How do we get low currents? We said that a transformer transforms voltage, but remember, as the voltage transforms, so does the current. So we want really high voltage in our power lines so that we get really low current. And you already know that power lines have really high voltages. That's why you don't want to touch them, because that voltage is going to let that electricity jump over big gaps in the air. There's tens of thousands of volts that flow through the power lines, hundreds of thousands in the really, really tall ones. So we have our coal power plant. Here we go. It's burning coal. It's a couple of 100 kilometers away. Here's all those greenhouse gases coming out of them. From that coal power plant, the electricity goes into a transformer. We're trying to get higher voltage so that we have lower current. So we have a step down transformer. Okay, so wires into the step down transformer, step down into your power lines. Power lines are held up really, really high on insulated poles, bit of insulated ceramics, so that the high voltages can't get anywhere. They just go through the wires. However, you don't want 10,000 volts of electricity coming out of your power points, because when you walk past, they'll shock your feet. So when the electricity comes back down, we need another transformer. Drawing my transformers in green, there is a reason. We need a step. Here we need a step down transformer, because I made a mistake over there. Over there we need a step up transformer. You know why I got it confused? I was thinking the current needs to go down, so it's a step down transformer. But transformers, always about the voltage. It's stepping up the voltage, really high voltage in the power lines. Okay, we have a step down transformer here to go into your home, school, or wherever. Right, this is a home. So electricity goes into the step down transformer into your home. That's how they're used for the distribution of energy in high voltage transmission lines. But you'll find transformers in other places. I'm using my laptop here at the moment, and the laptop is plugged into power. Oh, nope, I can't. This one. Plugged into power, it's got one of these. This is a transformer. The laptop can't handle the 240 volts that come out of my wall socket over there. So this thing transforms it to a much lower voltage. If you actually read all of this jazz, you can find on there somewhere it says 240 volts gets transformed to 20 volts. Okay. If you're not watching this on a computer right now, you're probably watching it on your phone. Maybe your phone is currently plugged in with one of these. This bit here is a transformer. Your phone can't handle 240 volts. Look at the bottom of this. It will tell you, well, this one tells me 240 volts turns into about 5 volts for my phone. Another fun fact on this as well as transforming the voltage, it's also a rectifier. That means it changes AC into DC. So when you look at it, the AC symbol, the 240 volts, is going to have a squiggly line to represent AC, but the DC, the 5 volts, is going to have a straight line representing DC, which I think is pretty cool. You also find transformers in other devices. Your microwave will have a step-up transformer because it needs high amounts of energy in it. It needs high amounts of voltage. In fact, when you lift a microwave, they're pretty heavy, but most of that weight comes from the transformer, from that iron core, really, really heavy stuff. Don't break your microwaves open, really quite dangerous. Old TVs, they'll have transformers in them. There are other devices as well. That's all for transformers. See you all later.